6. So, Roger, it is all yours. Thanks.
Thank you, John. Good afternoon. I'm glad to see all of you. And we're going to be talking about doing short circuit calculations. I want to start out, however, talking about short circuit damage. I have had an interest in electricity since I was very small. Started doing my first experiments when I was young enough to not realize all the things that were going to happen. And sometimes it's what you don't know is dangerous. And so what we're going to start out with here is just a little demonstration of what can happen as a result of the current that passes through anything. And all I've got here is, this is a test current generator. It's primarily used to test circuit breakers, fuses, that sort of thing. This can generate about 300 amps at low voltage. It's not the voltage that we're going to see the results of. What we're going to see is what the current will do to a small piece of conductor. Now this conductor is the same conductor that's feeding this light that's on right there. Okay, you've all got those running around your house, extension cords. Number 16, number 18 wire, depending on the quality of extension cord you bought. And so at any rate, what I want to do here is just show you what current can do in a short amount of time. Now the insulation's gone off of that in several places, and it stinks a little bit. Hopefully it won't cause any fire alarms to go off if the ventilation system works quickly. But most of the time, we don't think about what can happen when we have a short circuit with electricity. And so I want to just start out with a little bit about, what kind of damage you can have. Pow, blam, kaboom. Sounds from a Batman movie or during short circuit damage. It's interesting what can happen during a short circuit. The effects, I wish I could take all of you to a test station that the company I used to work for has. They've got a couple of them. One down in St. Louis, Missouri would be the closest to us, where they can generate about 300,000 amps at 600 volts. And huge transformers and things that do things. Because watching it, seeing pictures of it, is not the same as being there and have the hair on the back of your neck stand up and smelling what took place and hearing it with your ears. It's pretty impressive. But it can happen with small pieces of equipment. With electronic equipment, you can have short circuit damage. With motor control equipment, a little larger equipment, you can get into large pieces of switchgear. My first day on the job in Michigan, I had to go look at a piece of switchgear that looked like that and had people ask me, what caused this? How can we keep it from happening again? And that's what we're going to look at, is what do we have to do to keep these kind of things from happening. This last slide is a picture of a mannequin in front of a test looking at arc flash damage of what can happen when you get a screwdriver in the wrong place inside of a piece of switchgear. So, lots of forces there. And we're going to come back and talk about short circuit current calculations in a few minutes and look at the math and how we do the math to find out what kind of fault current is available. Today, more requirements are in place that people have to, when they build a facility, they have to label the equipment more today than ever before with the kind of fault current that's available, short circuit current that's available. And then equipment is sized to withstand what can go through it. Just like that piece of wire, if I had a heavier piece of wire, it wouldn't have smoked like that if it was rated to carry the 300 amps that just passed through it. But it wasn't, so it did. So we'll look at what happens when we have a short circuit like that in just a minute. But now I'm going to flip over here to another presentation. And this was provided for us to see from my former employer, and it is at the test station in St. Louis where they ran these tests using different kinds of equipment. But there are all kinds of requirements in the codes and standards in terms of ratings for electrical equipment. And one is the interrupting rating. That's the rating at which switches, fuses, circuit breakers, contactors, everything that has to break current, turn it off, has a rating for what's the maximum short circuit current it can stop. And you can't exceed that rating or you will end up with catastrophic damage. Current limitation is what we use specific kinds of devices for where the fault current that's available is higher than what the equipment it's going into can stand. So if there is a short circuit, it'll end up looking like some of those pictures that we saw a few minutes ago. So you want to be able to limit the current in some situations, so you use a fuse, current limiting circuit breaker, or some other medium to limit the fault current. One of my first experiences where I was involved with a situation where something was designed and a building was going in, a large facility, and at the last minute they did the short circuit calculations and the fault current was too high for the service that went into the building. And so what they ended up doing is having the utility company bury cable back and forth in front of the building to add resistance, impedance in the path before it got to the switchgear to limit the current. When we're taught in electricity courses, in electronic courses, in physics classes, they always talk about circuits where you've got a voltage supply and a resistance and various kinds of loads and things, but they never talk about the resistance of the wire. They just say ignore it, it's not there. But wire has resistance depending on the size. The larger the piece of wire, more resistance it'll have. And that resistance opposes the flow of current and can reduce it. So fuses are made with devices inside of them so that they can turn off current very, very quickly. And this is just a picture of some fuses here that have operated. This was the pre-operation, that's while it's arcing, and this is after it happened. This kind of fuse is put inside of a container where it has a metal, either copper or silver or combinations thereof, that melts at a high temperature. And when it melts, it creates an electrical arc, creates a lot of pressure inside that container. And then they put silica sand inside the container around that. And what happens under that arc and heat and pressure is that the silica sand turns into glass. And that glass process, making glass, takes the heat out of the arc, and the arc goes out very quickly. And so that's how it achieves the current limitation without any moving parts. This would be a misapplication. This is just a simple one-line diagram. The source is up here, and did the calculations and found out there's 45,000 amps of short circuit current available at this point. This would be like where the main service comes into this building for Grand Rapids Community College, where the switchgear is there. You'd have that kind of level of fault current available. And here we've got a fuse installed, 100 amp fuse that's in that switch box, branched off of it. It's rated for the voltage, but it's only got 10,000 amp interrupting capacity, and the fault current that's available is a lot higher than that. So that would be a general misapplication. And so this is what would happen to that fuse. This is under normal conditions. The fuse is sitting there, and then when it has a short circuit, it ends up looking like that. So in a very short amount of time, you do a lot of damage. Now let me show you what that looks like. In a video. So you wouldn't want to be standing in front of that. That's what causes an arc blast, that we call it.
This is a serious misapplication.
It is, serious. And so that can do a lot of damage for you. Now here's another situation where we've got the same fault current available, and this time I've got a circuit breaker in there, and this circuit breaker's got a little higher interrupting rating, 14,000 amp, but still well below what the available fault current is, just so that you can see what would happen to that. Should not have moved that. Okay, so there it is. And I don't know if you saw on both of these, there's just a short piece of wire at the bottom to create a short circuit right there, like if you were working there and you put a screwdriver across the contacts. So then this device is trying to break the current. What's it look like in real life? Now, the first time I saw some tests like this in the days before they created the newer test lab, they had a test lab that was right off of a utility generating station, and you stood outside to watch these tests. So you had to stand way back from them with binoculars so you could see the action.
Again, this is a serious misapplication.
But still, the forces involved were incredible. So if you have the device, however, that's rated for that level of fault current, here I've got a fuse that's rated for 300,000 amp interrupting capacity, well above the 45,000 amps available. And so when the test takes place, nothing happens. That's it.
Notice that the fault has been safely cleared without any damage.
So the test took place, and you couldn't even see anything happen. It turned off the current so fast that the fault current was reduced. So devices have to be labeled with this interrupting rating. And they come in various sizes, types, different levels of interrupting capacity. Generally, you pay more for higher interrupting capacity. But now I wanted to talk about this let-through current, I squared T and IP let-through. I squared T is just an abbreviation for ampere squared seconds. If we take the area underneath a waveform, it comes out in ampere squared seconds. If we integrate it and solve that integration in the time period that the current flows underneath the waveform, we end up with ampere squared seconds. And that's a measurement of the amount of thermal energy that's generated during the passage of electrical current. If we look at just the peak current squared, the peak current, then mechanical energy is affected by the peak current. So those two things do most of the destruction. So if this was normal current over here with a sine wave, and at this point in time a fault took place, and you see the current going 60 cycles per second, but it gets extremely high here in a very short amount of time. Now we'll come back and talk about this in a few minutes, but you'll notice this first half cycle much higher than the rest. And it's during that most of the damage is going to take place due to the mechanical energy of that peak current. But the thermal energy that represents that part that's shaded orange there will also do a lot of destruction and damage if it's not rated for it. So if we introduce a current limiting device, it will cut off the current before we reach that first half cycle peak, force the current back to zero. So we've got, if this is a current limiting fuse, you've got the time it takes to melt the element and then the time it takes for it to arc and clear the fault. But it's a short amount of time. If this is a 60 cycle waveform, which it is, and we're looking at 1/2 of 1/60th of a second approximately there, so we're well under that amount of time. That's a very, very short amount of time that the current flows. By controlling the time, we control the thermal energy that's developed. So we've got peak current for what was available, peak current for what passed through the overcurrent device. We've got I squared T that was available and I squared T that got through the overcurrent device. And we have tables that we can look at all of these data in order to size them to protect equipment in various applications. And again, the peak current squared is proportional to the mechanical energy, and the RMS current squared is proportional to the thermal energy. When we run these tests in the test lab, they actually do a graph of what takes place. And then we have equipment that will calculate the area underneath those waveforms, because when you have arcing going on, you no longer have a standard sine wave that you're looking at. So in order to come up with a I squared T that goes through there, it takes some specific calculations. Here we're looking at a situation where we're going to allow 5.5 cycles to flow through 90 feet of 2/0 conductor. Now, just so you can get an idea of what we're talking about, this is a 2/0 piece of wire. But that level of fault current, 45,000 amps, makes that look like a piece of spaghetti flipping around in the air. So that would just be the current flowing for 5.5 cycles. And then if we have a device that opens the current in one cycle, that whole first cycle is going to go through there. So this is a picture of the test setup inside the lab. Now today when we watch these tests. There's a bulletproof glass over here that you can't see, that you stand behind to watch the tests. And you're a little, you can see what's going on a little better and not exposed to damage like you were in past years. But now, watch the cable. This will give you an idea of the kind of mechanical energy from that peak current. Well, what happened here? I seem to have lost the link. Well, I'll have to come back to that. Both of them. Well, the test results, I'll come back and I'll get that to show at the end of the presentation so you can watch that. I can't explain why the computer lost the connection to pull those up right now. But we size different types of overcurrent devices depending on how well they will limit that fault current to restrict damage to equipment during fault current levels. So they're designed to do different kinds of jobs. You have different types of fuses and other overcurrent devices that will do that job. So a 75-degree rated conductor has ratings then for how much I squared T it can stand based on different test methods. And there's 3 different tests here. You can see different levels based on the way it was tested for a piece of number 12 copper wire. So we can run a test and see what will happen. Now the conductor feeding that would look like that during the fault current. With the current limiting device, nothing happens. So it's to the person's advantage that's working on a piece of equipment to be sure that it's rated so that they won't get that arc flash taking place in front of them. That's a requirement today for electrical equipment, that they have to test for that and rate the equipment to be able to protect people from being hurt. And they have limits then on how close you can work to this equipment to protect yourself. And that's just, again, a picture of the test that took place. Now, in terms of arc flash, how many of you have stood in front of a circuit breaker and turned it on, or changed a fuse in your home, or had that panel door open and stood there? You don't think about what can happen. And so you may want to think about that a little more the next time you're going to change something electrical, especially if it's an industrial application, so that you can avoid having that happen in front of you. Now, these are 3 different tests. In this first test, test number 4 here, test 3, test 2, but in this test that we ran, you have to be 47 inches away from where the arc is at so that your skin's not burned, so that you're not affected by the arc blast. In this one, you have to be 22 inches away, and in this one you can be as close as 6 inches. And it's different types of overcurrent devices that are being used that made the difference. So let's see here. Well, the best laid plans, you know. Sometimes with equipment, you can't do that. But I can get to the videos and play them a different way here, I think, in a few minutes. So back to short circuit calculations. So what What we do is if we do the right math, we can have equipment sized to prevent damage. That's the goal. We want all equipment to be able to handle whatever fault current's available, as well as what normal current passes through the equipment. And so we can do calculations to find out what kind of fault current's available. So in this little diagram here, a one-line diagram, source is up here, and down at the bottom I've got a fault that's taking place. Now, when that happens, what we really have to realize is that the current is flowing through the source and through that system, through the fault, back to the source, and so we have to come up with a way to be able to calculate all of the impedances that would slow down the current, that would limit the current in that kind of circuit. And it gets difficult because you have to go back and look at the source impedance, what can be supplied, as well as all of the resistances and inductances and capacitances that are in the system that create impedance to limit the current. So this kind of calculation used to be a scary thing. It's not as scary as it used to be because of the use of computers to do most of it today. But we used to do all of it by hand. So why do we do them? Again, back to the having to have the overcurrent device rated to stop the fault current. It's got to have enough interrupting capacity. Current limiting devices are sized based on the available fault current. You go and look at curves for different current limiting devices to find out at what level of fault current how much will go through the system, and then you rate the equipment to be able to withstand that level of fault current. Now, as you can well imagine, if you have to buy, for example, a motor control system where you've got push buttons to start a motor, if it's only rated for 20,000 amps, it's going to cost a lot less than if it has to be rated for 50,000 amps, because they have to use heavier duty equipment inside of it to be able to handle the higher current. So by using the current limiting device, you can limit the cost of some of the other equipment and save money that way. So we look at what the current limiting devices will do. We look at component withstand ratings, that is how much fault current each kind of component in the system can stand, every conductor, every contactor, everything that's in the system. Selective coordination is another thing that has to be considered, and that is when you have a fault, you want the device closest to the fault to open. That doesn't always happen. It has to be taken into account doing the design of the system to be able to set the overcurrent devices so they trip appropriately so that only that device closest to the system will shut down. If that is not set up that way, you can have situations where you can have a fault in one part of the building that shuts off the main to the building. Now you can imagine if you plugged something in this classroom and the overcurrent devices weren't coordinated and it turned the power off to the building if it was shorted out. That would not be a good thing. That has happened before in large buildings like this. And especially with the advent of newer equipment that does ground fault protection, because ground fault protection equipment measures the current flowing outside the system through the natural ground system, and it looks at the difference between the source current and what didn't come back on the neutral, and so something went wrong. We've got to turn the current off. And so it'll turn off at lower level fault currents. Most of you are familiar with a ground fault circuit interrupter in your home today. Anybody ever trip any of those in their home? Usually got a button to push to reset it. Those are set to trip at 5 milliamps of ground fault current, current flowing outside the normal system. In other words, on your single phase residential application, current's coming in on the hot line, the power line, and it's going back on the neutral. So what comes in goes out. It's a flow that's easy to measure, to compare the two and see if anything disappeared. And that's what a ground fault circuit interrupter does. It looks at the current on the two conductors and compares them. And if there's a difference of 5 milliamps, it turns off the circuit. Reason for that? You can go into defibrillation at just over 5 milliamps. Your heart quits beating properly. And you can go into cardiac arrest. When those devices first came out, they were set at 10 milliamps. Discovered not too long after that 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 wasn't adequate, so they lowered the standard to 5 milliamps to be able to cut off the current. That's 5 thousandths of an amp. And it's not the amount of current going through the circuit. You may have 20 amps going through the circuit, but it's that amount that flows outside through the resistance in a body then that the device senses. All of those things have to be taken into account to end up with the right kind of selective coordination. We also have to size the equipment grounding conductor so that it can handle whatever fault current's going to flow through it. Otherwise, it'll burn off and you lose the ground, and then you have another problem where you can get a serious shock by touching the equipment. And then, of course, the arc flash specifications today in terms of protecting employees that all of the standards are looking at to set that equipment. So, in order to do in order to do short circuit calculations, we have to first start out with a diagram of the electrical system. And normally to do these, we only do one line. We represent all of the conductors with one conductor. And then on that, we place all of the sources of short circuit current, any motors, any inductors, transformers that may also supply current to the fault. We look at component information, general information that's available on what equipment is rated for and what it has inside of it. And we need to have accuracy to be able to do the calculations, or what we end up with is an answer that's not a good answer. I just had someone ask me in a math class the other day, why do you have to be so particular? Why isn't 0.47 as good an answer as 0.52? Well, it can make a big difference in the results. And so we have to have that level of accuracy in our math. Now, the sources of fault current, the utility company supplies power to a facility, your home, for example, through the service entrance that comes into your house. And so there's a certain amount of fault current that comes from the utility company based on the size of their generators. The generators, if you have additional generators on the system, they can supply fault current as well. So those have to be looked at. Motors. Now, I showed you a picture before of how that fault current is so much higher during the first couple of cycles. Every motor that's running, when you have a short circuit and you force two conductors together, guess what happens to the voltage between those conductors? It goes away. It drops. And the motor all of a sudden has no applied voltage, and it doesn't continue to run like a motor. It says, I don't have any power, I can't run. But it still is rotating. It still has a magnetic field. And what happens is, as it's rotating with a magnetic field around the coils, it becomes a generator generating current into the fault. So we have to take all motors into account that are sizable as well in terms of our calculations, because they feed into the fault system. And then capacitors that are on the system that will discharge when a short circuit takes place. So all of those things have to be accounted for in terms of doing the calculations.
Pardon me, your description of the motor, does that mean that when that current cut off to it but it was spinning, it's just acting as a generator for a few cycles?
Until the field collapses.
Okay.
Yep. Yeah. Exactly right. So this is a picture of, here's our standard symmetrical current in the dark waveform, 60 cycles per second of a fault current. And that's a 50,000 amp RMS fault current. But during this first half cycle, the peak is much higher due to all of those contributions to the fault current. And it's not just the motors and the transformers that have fields collapsing. Every wire that's in the building has a little bit of additional response that it gives to that fault, because the fields, magnetic fields are collapsing around all of those things. So it makes all of the calculations a little bit complicated in terms of coming up with how high is this going to get. So we have to look at the X over R ratio, the impedance versus the resistance, because they operate at a right angle. And so we have to look at Pythagorean theorem in terms of calculating what the resultant impedance is as we do that. And so we have to look at kVA, and every transformer is rated with something called its percent impedance. And basically how that's determined is that a transformer is rated to deliver a certain amount of current. If a transformer is rated to deliver 100 amps to find out its percent impedance, they hook up a variable power supply ahead of it and increase the current until they get 100 amps out on the secondary side. And they look at the difference between the input and the output to come up with the percent impedance. How much will that transformer change the current during a short circuit is determined by that percent impedance. We have to know all the conductor sizes and their length. We have to know what type they are, what resistance they have. Cable comes in various sizes. This is just a piece of THHN that I passed around here, fairly stiff wire. And different kinds of wire will have different insulation and it'll affect it. We have to look at what kind of bus type it is. And busway is the devices that carry current other than a standard conductor like that. Sometimes they just have solid bars of metal. And the conductors inside of those have resistance between them, but then they put a metal case around it to protect you from contacting it. And that becomes another magnetic source as they build that. You have to look at whether they're 1 or 3 conductor cables, and then whether they're copper or aluminum. All of that affects the results. So these are the different methods that are used to do short circuit calculations. The ohmic method is the one we're going to look at here in just a minute. This is the IEEE standard method that's recommended for doing short circuit calculations. And so most computer programs work off of the data that's been developed to do that type of ohmic calculation of the fault current that'll take place. The per unit method, because these resistances get very small, 0.00002 ohms, so the per unit method takes everything and refers it to a common base so that we can move the decimal point. It's like a proportion problem. And so then we take that into account in doing the calculations, but it makes the math a little bit easier to do. The point-to-point method is a method that's only been around for about the last 20 years. And that method was developed using standard averages of what would happen in terms of a lot of the parts of the system, so that rather than do a true short circuit calculation, we're doing an approximation, but it's very accurate. And that one is used most commonly by people. If you're interested in looking at that, a lot of times when I talk about this, people will say, well, what about my home? And want to look at that. But if any of you are interested, I do have some printouts of how to do that point-to-point method of short circuit calculations if you're interested in it. And then finally, computer software. Bussmann's a pretty large company. If you go on the computer and Google Bussmann and go to their website, there's an online computer program that you can get into to do short circuit calculations, but you still have to feed it all that data. And so all of that goes into it, and it takes quite a bit of time. The ohmic method is a complex system because of the small numbers. You have to do some vector analysis because the impedance squared is equal to the resistance squared plus the inductive reactance squared. And so we have to take the square root of the sum of the squares of the resistance squared and the inductive reactance squared to find out what the impedance in the circuit is. Then we have to look at polar coordinates for reactive impedance, and it's a very accurate system because everything's accounted for. And so in order to do a short circuit calculation on a standard industrial system, we'd have a one-line diagram that we'd start with. And this starts out with asking the utility company right here at the source, okay, if we have a dead short in our facility, how much current can you deliver? And that's usually given in terms of megavolt amps, how much power that utility company can deliver. And then you have to know the size and distance of the conductors to the main transformer, the size of the transformer in terms of its kVA rating and the different impedances that it's rated for. The X and R ratio of the transformer then can be calculated. But then you have this percent impedance that I talked about before, so you can look at how much this transformer will contribute to the fault. And then you have to know the full load current rating of the transformer. Then we've got 25 feet of 500,000 circular mil conductor. That's a very large conductor. 6 per phase. They're run in parallel on this system. And it feeds down to the service entrance where the main switch is. and then there's a 2,000 amp switch and a 2,000 amp fuse that's installed. And so we want to look at what happens at this fault current. If I have a short circuit right there, right by that main switch gear, how much current will flow? So that becomes the challenge then, to go back and take the data, put it into the proper form and do the calculations to see if we can find out what kind of fault current's available. So I take that one-line diagram, and then after I've got that finished, I do an impedance diagram so that I can write in then all of the different impedances involved in that system. And so we'll add to that and use the data then to calculate the inductance and inductive reactance characteristic then for each component in there, and the resistive component as well. So as we do all of these calculations, and so basically what this is doing, this is the voltage here in terms of kVA. 480 volts in kVA is 0.48 kVA, kilovolts, and then multiply it times 1,000 to get it back to where it's supposed to be. And then this is the base number that's used for the calculation, 100 million. And when we do the calculation for that input, we find out 0.000023 inductive reactance. That's pretty small. Not a lot of resistance to the flow of current. But we have to do that then for each of these components and complete the calculations. So these are just standard electrical formulas that are used to calculate the impedance in this system. And once we do all the calculations, then we bring those over into a table, so I can add all the resistances together and all the reactances together, and I end up with a total resistance and total reactance, inductive reactance. And so that's what's going to impede the fault current. Now I take those numbers, okay, the total resistance and the total inductive reactance, the opposition to the flow of current, and then we do the Pythagorean theorem to calculate what is the total impedance to the fault current. Now because this is a three-phase system, we're dividing by the square root of 3 times the impedance that we get here, 0.0056 amps. We're going to take on the bottom, the voltage is on the top. Voltage divided by resistance will give us the current flow. And so when we do the calculation, we find out that you can have 49,489 amps of fault current there at that main service switch. So it's a matter of taking all of the parts of the system and doing a calculation like that for each one of these. But then we've got the contribution from the motor that has to be calculated in too. We had 4 motors that were running, large motors, and so this is 4 times the full load current that they had available. And so the motors can deliver another 7,216 amps to that fault. So we add those together to get a total fault current available at that point of 56,705 amps. Then we calculate the X over R ratio, to come up with an asymmetrical factor, so how much that's going to be offset in that first half cycle. And there are tables that are provided to do that with. And then we can calculate the asymmetrical RMS current that's flowing in that first half cycle that will decay then over several cycles. Add that to the motor contribution. And so the RMS current of that first half cycle is 73,059 amps. So at that point, we have calculated here at fault 1 the RMS fault current, but we also have to look at the asymmetrical fault current to look at the equipment ratings. So what we do then is we move on and we have to expand the system and add in the other impedances to our already completed diagram to get to the next fault, and then we'll go back and add all the resistances, all the inductances, and do the same kind of calculations to come up with the fault level at the next point. And here, because of the resistance and inductance in the system, it drops down to 42,837 amps. So what that means is whether I put a fuse or a circuit breaker in here, I have to be able to stop, to interrupt that much fault current, or it's going to fly apart. And so that's the reason why we do the calculations. And then we look at various types of equipment beyond that. The per unit method it makes it a little simpler because of the changing of the decimal point, makes the math a little easier, but it's basically the same calculations. And then today, most of the time, to provide simplicity so that people aren't spending all their time doing math, they either use a computer program or many times use the simplified point-to-point method to do the calculations. So the point-to-point method has simpler math. The vector analysis is simplified. You don't have to do that because they're using averages to accomplish that. And it looks at worst-case conditions and uses impedance averaging. We get reasonable accuracy and simplified calculations. So this is the same thing doing the point-to-point calculation. So what you do is you calculate the fault current at this point, then you take the impedances to the next point and you multiply, you come up with a multiplier to, so if this is 85% at this point, you multiply the first one times 85% to get here, and if this drops another 50% to get here, you multiply that last one times 50%, and it just makes it a lot simpler to do, to be able to do the calculations. Whoops, didn't mean to do that. Okay, so a comparison of the results. This is the ohmic method. Without motor, with motor. The per unit method. Same numbers. The short circuit calculation done by the computer, pretty close as well. And then this point-to-point method is not very far off from the others. So it gets you close to the right number. It's generally used to size equipment. It can be done in the field, really, when someone's working on a piece of equipment trying to come up with an idea of why this needs to have better protection or why it didn't have the right amount of protection. It allows you to get a quick answer for that kind of a question. So short circuits are available. Computer programs are available to do that, but like I said, you can go online and do it for free, so why would most people buy the computer program anymore? All right, let me see if I can get that video to run on the wire. I really wanted you to see that, if I can find it here.